Hello, students. Today we continue where we left off yesterday. If you recall, we have been talking about the sun, our favorite star of the solar system. In fact, it's the only star in our solar system. It is the star that holds our solar system together. Now, the solar system is next week's topic, and right now we're just focusing in on the sun. Yesterday, if you remember, we discussed the structure and temperature of the sun. And we left off yesterday getting into some of the solar activity that takes place because the sun is such a dynamic and violent location in our solar system. So let's begin today by talking about solar activity. In fact, there are 5 different kinds of solar activity that we are going to address today. The prominence, solar flare, sunspots, solar wind, and finally the CMEs, which is a short way of writing coronal mass ejections. And we'll get to that last as we begin discussing the various forms of solar activity. Before we get there, let me just mention something. Do you see this image here? This is an actual photograph of the sun. This is what the sun really looks like. Now, this one down here, that's just a diagram, an image. This one is an actual photograph. In fact, I'm going to be showing you today actual imagery of our sun, taken with special telescopes and special filters that enable us to see things in great detail. But if you look at the surface of the sun, this is not a place you would ever want to visit. It is a violent place. However, as we all know, it is the sun that keeps us alive and sustains life on planet Earth. 150 million kilometers away from our planet, we are entirely dependent upon the sun. All of these activities and more allow life to exist. So let's begin with our first solar activity, which is called a prominence. This isn't the most prominent activity on the sun, but prominence are huge, bright arches or loops of gas. Let me put this into perspective for you. Again, this is an actual image of the sun, and depending upon the lighting in the room, you may or may not be able to see the prominence. So I actually outlined it in a red marker here. So these red lines indicate the bright arch or loop of gas which is being thrown out from the sun. And for scale, I added a little blue dot, which is about the size of planet Earth relative to the size of the sun. In fact, you can fit 100 Earths side by side along the diameter of the sun. So this Earth is probably maybe even a little too big relative to the size of the sun here. But I put it here to give you a scale of reference. Look at the size of this prominence. It is hundreds of times bigger than our entire planet. Think about that for a moment. This little loop of high energy gas extends many times out beyond the dimensions of our tiny little planet here. But I want you to keep a couple things in mind. Number one, the Earth is never this close to the sun. So don't worry about prominences destroying our planet. You know, if at this scale, If the sun were this big, the Earth would be on the opposite side of the school. That's how far away the Earth is from the sun. But I put it here again for a scale of reference. So, what exactly is a prominence? Why are these huge bright arches of loops of gas? Well, imagine playing with a magnet. How many of you have ever seen? Oh, I wish I had one here with me. How many of you have ever seen those bald guys and the little magnetic wand, and you bring the iron filings and put it all over his face? I mean, that's like fun stuff, right? But if you've ever played with iron filings and a magnet, in fact, I think we did this in the geology unit. So think back to when we did that. But if you do that, you may notice that the iron filings take on a shape like a loop at either end of a magnet. It's because they follow the magnetic forces that exist around that magnet. It's an invisible force, but iron filings enable you to see it. Well, the sun is so supercharged. Not only is it exerting a massive gravitational force on the entire solar system, holding it together, but it's also, because of its high energy state, it is exerting incredible electromagnetic forces. And sometimes these forces surface to the top and spews out some supercharged gases, and these gases, like the iron filings, illustrate the various magnetic fields and the electromagnetic fields as they exit the sun itself. And that's exactly what a prominence does. It mimics or follows the electromagnetic forces. And we're going to be seeing some other features here as well. In fact, I want you to look at where this arch uh, begins and ends, and you'll see these brighter areas. We're going to be talking about those brighter areas, and it's typically those brighter areas where a prominence either begins or ends. In fact, speaking of those brighter areas, let's go on to the next one, which are solar flares. You've probably all heard of the word flare before. A flare can be used on the side of the road if you break down. Police or emergency squads may put a flare on the road, and it shines bright, especially at night, so that other drivers can see. You might have a flare gun. If you're lost at sea, you shoot a flare gun, sends a bright light into the sky, so hopefully somebody can rescue you. Well, a solar flare is a burst of light on the photosphere. And you remember the photosphere from yesterday. Now, this bright burst of light has a temperature that is typically 2 times as hot as the surrounding area. Now, do any of you remember the temperature of the photosphere that we mentioned yesterday? If you do, call it out. About 6,000 degrees Celsius, right? So if that's the temperature of the photosphere, how hot do you think these solar flares are going to be? Yeah, 2 times that, about 12,000 degrees Celsius. That's pretty hot, very hot, in fact. And because they are so hot, they get very bright. So you can see in this image here, which again is an actual photograph of a solar flare on the surface of the sun, this bright area here is the solar flare. And this is a flat image, but imagine it was three-dimensional. This portion of the flare is actually spewing up into space, creating a prominence, our last solar activity. So solar flares and prominences typically go hand in hand. They are related to one another. And again, these solar flares are hot. They are related to a lot of solar activity on the photosphere, which results from those convection currents we talked about yesterday. Remember, here on Earth, our weather, the winds, air pressure, storms like hurricanes and tornadoes are all a result of just a few degrees difference in temperature. Here on the sun, we've got millions of degrees differences, so you can imagine the strength of the storms that exist on the surface of the sun. They are a lot more powerful and damaging than the strongest storm could possibly ever be here on Earth. And so, speaking of storms, let's go on to the third type of solar activity, which are called sunspots. Sunspots are dark, cooler areas on the sun's surface. Now, for scale, I've drawn a blue circle here to represent the size of our planet Earth. So the Earth is never this close to the sun, but this is an actual image, a photograph of the surface of our sun. And you can see that it's not completely uniform. There are some dark spots that we call sunspots. And they are dark because they are cooler than the surrounding area. This area on the photosphere, about 6,000 degrees Celsius, pretty hot. But cooler areas are going to be darker. They don't give off as much light. Now, solar storms, these sunspots that are indicative of solar storms, they tend to appear in cycles. You see, the sun has a magnetic field, kind of like the Earth does. And the sun's magnetic field flip-flops about every 11 years. So there are 11-year cycles that exist on the sun. So about every 11 years or so, the North Pole becomes the South Pole and the South Pole becomes the North Pole. We're still trying to figure out why. We don't completely understand why this happens, but we've observed it for a couple hundred years now that the magnetic field of the sun flip-flops about every 11 years. Now, on Earth, you may recall when we studied geology and the mid-ocean ridge, mid-ocean ridge, mid-ocean ridge. I know some of you remember that song from earlier in the year. Anyway, if you think back to that geology unit, we learned how the Earth's magnetic field flip-flops as well periodically. Not every 11 years, more like every 1,100,000 years. I forget exactly what the time span is. But as the mid-ocean ridge divides or separates, we can see the deposits of the lava, creating igneous rocks, take on the characteristics of the magnetic field when it emerges from the Earth's crust. And every period of time, we can see that the magnetic field of the Earth flip-flops as well. But certainly not every 11 years like the sun. The sun's flip-flopping of the magnetic field, and you might want to write that down next to sunspots too, about the flip-flopping magnetic field, because this is very important. Because you see, when there are these cycles of magnetic fields flipping, there are also cycles with the storms that exist on the sun. So every 11 years during this cycle, there is an increase and then a decrease in solar activity. When there is an increase in solar activity, and it happens around the time that the magnetic field flips, there's an increase in storms, there's an increase in sunspots, there's an increase of prominence, and there is an increase of solar wind. This solar wind, which is a continuous stream of high energy, emanating from the corona changes. And during this 11-year cycle, sometimes it is extremely powerful and can do damaging things to the Earth, which we'll talk about in a moment with our last solar activity. But I want to pause here on solar wind, this continuous stream of high energy from the corona. By the way, this is a picture of the sun during a total solar eclipse. So the dark circle is actually the moon. The moon during the new moon phase, and we've learned about the moon phases earlier in the year. So during a total solar eclipse is when we can actually see the corona. And check out how the corona of the sun is spewing this solar wind out in all directions. Now, some scientists are actually suggesting, and we've actually experimented with this, believe it or not, about propelling rocket ships using solar wind. Yeah, it's actually been done on a smaller scale. Some want to really build up the scale. You know, a few hundred years ago, travel around planet Earth was entirely dependent on the wind with sailing vessels. And we were, and still are, able to sail around the entire planet using nothing but the wind here in Earth's atmosphere. So some scientists thought, hey, there's this thing called solar wind, which is always coming out from the sun. Why not build a rocket ship with a big sail on it? Now, that may seem kind of a silly idea, but believe it or not, it actually works. We have recently sent a satellite into space that deploys a solar sail, not unlike a sail here on Earth on a sailboat. And the wind from the sun, which, by the way, is not the same kind of wind here on Earth. Solar wind is this stream of high energy particles like protons and neutrons being spewed out. And these particles are what push on the sail and move it through space. The other day, I demonstrated the radiometer to you in class. And perhaps today, if it's a sunny day, I'll bring the radiometer out and show it to you again. And as you know, that radiometer are like tiny little sails that are pushed around by particles of light. Pretty cool stuff. Pretty cool stuff. So solar wind is something that might be a positive thing for human beings. Some are also suggesting that as we return to the moon, maybe solar wind could be tapped into in order to generate electricity. Another topic for another day, but let's move on to the really dangerous one here. And those are the coronal mass ejections. A coronal mass ejection, summarized as CME, are unusually large releases of plasma and magnetic fields from the corona. They happen, again, during periods of high solar activity. I mean, we can see a prominence here. We can see sunspots and solar flares, etc. But a coronal mass ejection can be very dangerous here on Earth. Let me explain why. We have developed a very technologically dependent society. This has only happened in the last 100 years or so. Prior to 100 years ago, nobody even had lights in their home, much less computers and cell phones and all of the other gadgets that we depend upon to live our daily lives, for financial institutions, for acquiring our daily food, from travel and so forth, commerce, airplanes flying. I mean, you name it, every form of transportation and commerce today is dependent upon technology. Technology that utilizes electromagnetism in one way, shape, or form in order to work. Even the production of electricity is dependent upon electromagnetism. Whether you're burning fossil fuels or using solar energy, they both involve electromagnetism. So, what's the big deal with a CME or a coronal mass ejection? Well, this unusually large release of plasma and magnetic field from the corona of the sun travels about 1,000,000 miles an hour through space and hits everything in its way, including planet Earth. All right, big whoop-de-doo, right? Well, we have a magnetic field here on Earth that helps protect us from such things like CMEs from the sun. In fact, the aurora borealis are the visual result of seeing this magnetic field and these highly charged particles hitting the Earth and us being protected by the ionosphere. And you see glowing lights in the sky, the aurora, both in the north and southern hemispheres near the magnetic poles. But sometimes a coronal mass ejection is so powerful that it cuts right through our magnetic field, which protects us. It happens, and it has happened. A number of years ago, a burst of a coronal mass ejection caused a complete blackout in eastern Canada, knocked out all of the power grids. And that was probably 30 years ago. Even 100 years ago, when people were still relying, well, maybe 150 years ago, when people were still relying on telegraph, the dots and dash. Even before the major utilization of technology like we have today, there was a coronal mass ejection, a big one in the late 1800s, that caused telegraph operators to catch on fire because of the massive magnetic field that was just traveling through the telegraph wires. Now imagine, and we don't even have to imagine because it's going to happen, it's inevitable during these cycles of the sun that we're going to get another massive coronal mass ejection. Imagine our power grid today. Imagine daily life today receiving this incredible amount of energy from the sun. I don't want to be a doomsday sayer, but think about the impacts. Maybe we could discuss that when the lesson is finished, because we want to move on. Let's move on, but do think about our dependence on technology and how the loss of that technology in an instant for an extended period of time would affect everything during our daily lives. But let's finish today with a brief discussion of the life cycle of the sun. As you know from last week when we studied stars, stars go through periods of growth and decline, and our sun is no different. And so we're going to talk about the different components here of the life cycle of the sun. I like to call it the 10 billion year battle of the bulge. I'm battling the bulge in my midlife years here, as I tend to be a little less active and tend to eat a little bit more. I got the battle of the bulge going in my belly. But the sun is a midlife star, and it is experiencing a battle of the bulge as well. There are these constant forces at work with any star, our sun included, between pressure and gravity. You see, gravity, because of the mass of our sun, has so much mass, the force of gravity is pulling it in. But as we've talked before, that massive force of gravity pulling all of the particles in is what ignites that nuclear fusion. The nuclear fusion then is pushing outward in all directions, and it creates a pressure. The sun and any star is battling between those two forces, the pressure pushing out and the gravity pulling in. It's what allows a star like our sun to have a spherical shape, because these forces are acting not only in opposite directions, but equally in all directions. So that's why the sun is a sphere. Now, here's the deal. Eventually, our sun is going to run out of fuel. And when our sun runs out of fuel, it is going to stop the nuclear fusion reactions. And when that day arrives, which won't be for billions of years, so don't worry about it. Don't lose sleep tonight thinking that the sun is going to run out of fuel. May happen with a car, but not with the sun in our lifetimes at least. But when our sun runs out of fuel, gravity wins. What do I mean by that? Well, again, imagine the sun being squeezed in by gravity, being pushed out with the pressure from nuclear fusion reactions, causing the energy to go outward. Well, when it runs out of fuel, it's not going to be pushing outward anymore, and gravity is going to pull it in. So there will be a period of time, it is believed, where the sun will, near the end of its life, expand tremendously for a relatively short period of time, perhaps even turning into a red giant as it starts depleting. It's going to be like a sputtering engine as it starts running out of gas. And then once it does that, gravity takes over and it will implode and perhaps turn into a white dwarf. And so that is the life cycle of our sun. When the fuel runs out, gravity wins. By the way, it's what happens to most of us too when we get older. Gravity wins and pulls everything downward. That's why we get wrinkles and all that good stuff. All right, but enough of that for now. Tomorrow, we're going to actually measure how big the sun is. So read over your lab activity for tomorrow. And until then, I'm going to say bye-bye.